Today's learning focus is continuous random variables. This is our last probability chapter.
The last chapter, yeah.
The last chapter. Sort
We're
of.
not doing chapter 4.
So,
We're going back down to 4.
let's focus on this. So we started probability looking at discrete random variables. So the word continuous instead means what? If something's continuous if it's you measure it. So the word continuous tells us that we're measuring things. When you looked at discrete random variables, we saw that as a picture, we saw it as like bar graphs and that sort of thing. How do you think you'd see continuous random variables as a picture?
Oh, maybe like a parabola.
Parabola,
Bell curve.
bell curve. And so the key there is it's like a curve. So it's represented with a curve. Okay? No gaps between them. Continuous. Continuous line. If something is going to be shown in probability by a continuous curve, what are some important rules we know about probability?
Up to 1.
Up to 1. Can't be more than 1. That's very important. And so the way we show that rule,
Are you filming?
the way we show that rule is that the area, that is the area under the graph, the integral from two values, say from A to B. So if I just look at this section here, if I'm saying that this here is the picture of a continuous random variable, then the area from A to B, of whatever this function is, must be 1. It can't be less than 1, it can't be more than 1, it must be 1. So if the picture we're looking at, the curve we're looking at, is to show the probability of a continuous random variable, the area under the curve between our two values must be 1. It's a very important point.
Must be 1.
Must be 1. Another important point would be, what else do you know about probability?
Can't be negative.
Can't be negative. And what else? Maybe expand on this thought. Or put these two thoughts together.
1 minus.
All probabilities are between 0 and 1. So key facts there. And you're going to use those when you're answering these questions. So let's have a little look at an example. So you're going to be graphing a few curves today. And you're going to be looking at them as well. So if I have something like the integral from 2 to 4,
Oh, you're only just in the screen.
12 minus 3x
Can't
dx.
see it on your little screen.
Can't you?
Yeah, no, I think you just did.
Justin.
We're having some technical difficulties.
There we go. Thanks for that. Because this is really for Coco today, isn't it? Okay, so we've got the integral from 2 to 4.
That's sticky.
And if I'm saying that
Oh,
this here is representing a probability distribution
That lad
function,
is really pissing me off now, Tim.
we're filming. You're going live. You just swore on YouTube. I'll probably take it down now. So this integral is representing a, I tell you that it's a probability distribution function. If I tell you that, then that tells you that this here equals what? 1. And then the question would be, find A. What does A equal? So if A is a constant, that means I can take it out. So that's probably the first thing I do.
Probably.
Yeah. Then I do the integral, so A on the outside. The 12 would have come from 12x. The 3x would have come from 3x squared. What else do I have to do? 2, lovely. From 2 to 4. Substitute your numbers in. So 12 times 4 minus 3 times 4 squared over 2. Then what do I do? Minus. Substitute 2 in. Work out what all of that equals. That's just a bit of number crunching. So all of that comes out to 6. So I get A times 6 equals 1. Therefore, we get A being 1 divided by 6. So for that there to be a probability distribution function, a bit of a mouthful, for a continuous random variable, then A has to equal a 1/6. Any questions? The whole integral has to equal 1. That's what we've said here, the whole integral equals 1. And we don't know what number A is. So if that's going to be true, the question is, what does A have to be? So if A is a 1/6, that works. If A was anything other than a 1/6, it would work, it wouldn't equal 1. Good question. Happy? Nice. Well, let's get on with some work then.